The importance of thorough electrical inspections cannot be overstated. Even experienced inspectors can sometimes miss violations. Electrical systems are inherently complex, and overlooking details can occur, especially in unfamiliar or high-pressure situations. An experience highlights the significance of meticulously examining all aspects of an electrical system. It's crucial to look beyond the immediately apparent and to question anything that seems unusual or out of place. Each mistake serves as an invaluable opportunity for learning and improvement. Acknowledging errors demonstrates a commitment to professional growth and a dedication to preventing similar issues in the future. To mitigate the risk of such oversights, consider the following recommendations. Firstly, slow down during inspections. This is one of the most important things to consider. Resist the urge to rush through the process, especially when dealing with unfamiliar or complex electrical systems. Take your time to carefully examine each component and connection. Secondly, question unusual findings. Develop a habit of critically assessing anything that deviates from the expected norm. If something seems out of place or doesn't make logical sense, don't hesitate to ask questions and thoroughly investigate the matter. This proactive approach can help uncover hidden problems and prevent potential hazards. Thirdly, consult with others when needed. No one possesses all the answers, and seeking guidance from more experienced inspectors or qualified electricians can prove invaluable. Don't hesitate to tap into their expertise when faced with challenging or ambiguous situations. Collaboration and knowledge sharing are essential for maintaining high standards of safety and accuracy. Fourthly, meticulously document all findings. Comprehensive documentation is crucial for providing a clear record of the inspection and ensuring that any identified violations or irregularities are properly addressed. Include detailed descriptions of the issues, their locations, and any corrective actions taken. Such documentation serves as a valuable reference for future inspections and maintenance activities. An experience highlights the critical nature of neutral connections in electrical systems. The neutral bus serves as a crucial point for distributing the neutral current back to the source. When screws attaching the neutral bar to the neutral bus are removed, it creates a high resistance connection which can cause several issues. This can disrupt the flow of current and lead to a variety of problems throughout the electrical system. When the neutral connection is compromised, the load center might act as if it has lost the neutral connection to all circuits. This can cause voltage imbalances, where some circuits receive higher than normal voltage and others receive lower than normal voltage. This voltage imbalance can damage sensitive electronic equipment. A missing neutral connection can also create a shock hazard. If the neutral connection is lost, the metal enclosures of electrical equipment can become energized, posing a risk of electric shock to anyone who comes into contact with them. A compromised neutral connection can lead to overheating of conductors and connections. This can create a fire hazard and potentially damage the electrical system. The absence of screws can create a high resistance connection that can generate heat and cause the surrounding materials to ignite. In electrical panels, the neutral bar is typically connected to the metal enclosure, effectively grounding the enclosure and providing a path for fault current to return to the source, tripping a breaker or fuse. However, removing the neutral bus screws disrupts this grounding path, which can have severe consequences. If a fault occurs within the panel or connected equipment, the fault current may not have a clear path back to the source. This can prevent the overcurrent protection device, such as a circuit breaker or fuse, from tripping, leaving the fault condition unaddressed and potentially leading to equipment damage, electrical shock, or even a fire. Without a properly grounded enclosure, the panel itself can become energized during a fault condition. This poses a significant electrical shock hazard to anyone who comes into contact with the panel. In addition to safety concerns, the absence of a proper grounding path can interfere with the proper operation of sensitive electronic equipment. Electrical noise and interference can propagate through the system, leading to erratic behavior or malfunctions. The equipment grounding conductor, or EGC, plays a vital role in electrical safety. It provides a low impedance path for fault current to return to the source, facilitating the quick tripping of overcurrent protection devices. The EGC connects the metal enclosures of electrical equipment and appliances back to the main grounding electrode system, ensuring that any fault current flows safely back to the source. To ensure electrical safety and proper system operation, electrical codes and standards mandate the correct installation and maintenance of neutral and grounding connections. Electrical codes provide specific requirements for the size, type, and installation of grounding conductors, as well as the bonding of metal enclosures. Ignoring or neglecting these requirements can have serious consequences. Inspectors and electricians should be vigilant in verifying that all neutral and grounding connections are properly installed and maintained in accordance with applicable codes and standards. This includes checking the tightness of connections, inspecting for corrosion or damage, and ensuring that grounding conductors are properly sized and routed. Periodic inspections and testing can help identify potential problems before they escalate into major safety hazards. An inspector's experience serves as a valuable reminder of the importance of diligence and attention to detail during electrical inspection. By thoroughly examining all aspects of an electrical system, questioning unusual findings, and consulting with others when needed, inspectors can minimize the risk of overlooking critical safety issues. Additionally, continuous professional development and a commitment to learning from mistakes are essential for staying up to date with the latest codes, standards, and best practices. In a load side panel, the neutral bar is typically isolated from the panel enclosure. This isolation is crucial for preventing unwanted ground loops and ensuring proper operation of sensitive electronic equipment. In contrast, in a service panel, the neutral bar is bonded to the panel enclosure, providing a direct path to ground. This bonding is necessary for safety reasons, as it helps to quickly trip over current protection devices in the event of a fault. Electrical codes outline specific requirements for grounding and bonding electrical systems, including the proper methods for connecting neutral bars, grounding electrodes, and equipment grounding conductors. These requirements are designed to ensure that electrical systems are installed and maintained in a safe and reliable manner. Failure to comply with these requirements can have serious consequences, including electrical shock, fire, and equipment damage. An isolated ground receptacle is designed to reduce electrical noise and interference. It achieves this by providing a separate grounding path for sensitive electronic equipment, isolating it from the normal grounding system. The isolated ground conductor is typically identified by an orange color and must be run directly back to the grounding electrode system without any intermediate connections. The purpose of an isolated ground is to minimize the effects of electrical noise and interference on sensitive electronic equipment. Electrical noise can be generated by a variety of sources, including nearby electrical equipment, radio transmitters, and even atmospheric disturbances. This noise can interfere with the operation of sensitive electronic equipment, causing erratic behavior, malfunctions, or even data loss. By providing a separate grounding path for these devices, the isolated ground helps to reduce the amount of noise that reaches the equipment, improving its performance and reliability. The isolated ground conductor must be run directly back to the grounding electrode system without any intermediate connections. This ensures that the isolated ground is truly isolated from the normal grounding system. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods or ground plates, that are buried in the earth. These electrodes provide a low impedance path for fault current to return to the source, helping to quickly trip over current protection devices in the event of a fault. It is essential to verify that the isolated ground conductor is properly installed and connected in accordance with applicable codes and standards. This includes checking the tightness of connections, inspecting for corrosion or damage, and ensuring that the conductor is properly sized and routed. In some cases, it may be necessary to perform testing to verify the effectiveness of the isolated ground. The National Electrical Code, or NEC, contains specific requirements for the installation of isolated grounds. Section 250.146 D covers the requirements for isolated ground receptacles. It is important to consult the NEC and any applicable local codes and standards when installing or inspecting isolated ground systems. Electrical systems are designed to distribute power safely and efficiently. Understanding the different types of circuits, such as branch circuits, feeder circuits, and service circuits, is essential for ensuring proper installation and operation. A branch circuit is a circuit that extends from the lost overcurrent protection device to the outlets or equipment it supplies. Branch circuits can be either general-purpose circuits, which supply multiple outlets for lighting and appliances, or individual circuits, which supply a single appliance or piece of equipment. The size and type of conductors used in a branch circuit must be appropriate for the load it will carry. The NEC provides specific requirements for branch circuit wiring, including the minimum size of conductors, the type of insulation, and the methods of installation. A feeder circuit is a circuit that extends from the service equipment to one or more branch circuit panels. Feeder circuits carry a larger amount of current than branch circuits and are typically protected by larger overcurrent protection devices. The size and type of conductors used in a feeder circuit must be appropriate for the total load it will supply. The NEC provides specific requirements for feeder circuit wiring, including the minimum size of conductors, the type of insulation, and the methods of installation. A service circuit is the circuit that connects the utility power supply to the service equipment. The service circuit is the main source of power for the entire electrical system and must be sized and installed to handle the total load of the building. The NEC provides specific requirements for service entrance wiring, including the minimum size of conductors, the type of insulation, and the methods of installation. It is essential to understand the differences between these three types of circuits and to ensure that they are properly installed and maintained in accordance with applicable codes and standards. Neglecting these requirements can have serious consequences, including electrical shock, fire, and equipment damage. Electrical safety is paramount, and understanding the role of grounding and bonding is crucial for preventing electrical hazards. Grounding is the process of connecting the metal enclosures of electrical equipment and appliances to the earth. This provides a path for fault current to return to the source, helping to quickly trip over current protection devices in the event of a fault. Bonding is the process of connecting together all of the metal parts of an electrical system, including conduits, enclosures, and equipment grounding conductors. This creates a low impedance path for fault current to flow back to the source, ensuring that all metal parts are at the same electrical potential. The NEC contains specific requirements for grounding and bonding electrical systems. These requirements are designed to ensure that electrical systems are installed and maintained in a safe and reliable manner. Grounding electrodes are typically made of copper or galvanized steel and are buried in the earth. The most common types of grounding electrodes are ground rods, ground plates, and metal underground water pipes. The grounding electrode system must be properly sized and installed in accordance with the NEC. The equipment grounding conductor, or EG, is the conductor that connects the metal enclosures of electrical equipment and appliances to the grounding electrode system. The EGC provides a low impedance path for fault current to return to the source, helping to quickly trip over current protection devices in the event of a fault. The EGC must be properly sized and installed in accordance with the NEC. Bonding jumpers are used to connect together all of the metal parts of an electrical system. Bonding jumpers must be properly sized and installed in accordance with the NEC. It is essential to understand the importance of grounding and bonding and to ensure that all grounding and bonding connections are properly installed and maintained in accordance with applicable codes and standards. Neglecting these requirements can have serious consequences, including electrical shock, fire, and equipment damage. In electrical panels, the overcurrent protection devices, such as circuit breakers and fuses, are designed to protect the electrical system from overloads and short circuits. Overloads occur when the current flowing through a circuit exceeds the rated capacity of the conductors. Short circuits occur when there is an unintended connection between two conductors of different electrical potential. Circuit breakers are electromechanical devices that automatically interrupt the flow of current when an overload or short circuit occurs. Fuses are devices that contain a fusible link that melts and interrupts the flow of current when an overload or short circuit occurs. The NEC contains specific requirements for the selection and installation of overcurrent protection devices. These requirements are designed to ensure that the overcurrent protection devices are properly sized and installed to protect the electrical system from overloads and short circuits. The ampacity of a conductor is the maximum amount of current that it can safely carry without overheating. The ampacity of a conductor depends on its size, type of insulation, and the ambient temperature. The NEC provides tables that list the ampacities of different types of conductors. It is essential to select conductors with an ampacity that is sufficient for the load they will carry. The interrupting rating of an overcurrent protection device is the maximum amount of fault current that it can safely interrupt without being damaged. The interrupting rating of an overcurrent protection device must be sufficient for the available fault current at its location. The available fault current is the amount of current that would flow in a short circuit at a given point in the electrical system. The NEC provides methods for calculating the available fault current. It is essential to select overcurrent protection devices with an interrupting rating that is sufficient for the available fault current. Proper selection and installation of overcurrent protection devices are crucial for ensuring electrical safety and preventing equipment damage. Regular inspections and testing of overcurrent protection devices can help identify potential problems before they escalate into major safety hazards.